Hello, Honors Chemistry, and welcome to Chapter 9, where we're going to talk about light, how light behaves, more importantly, how light interacts with electrons, because that's what gives us information about how atoms look on the inside, right? And then we're going to put those atoms together and talk about what molecules look like at the particle or the microscopic level, right? It is a neat chapter. It is a chapter that explains a lot of the stuff that we've sort of assumed over the course of the school year, right? But it doesn't necessarily fit in terms of like how every other chapter sort of layers new information onto what we already know. This chapter is a little bit weird, as it sort of just like fills in pictures, okay? But no worries, we get right back into molarity, stoichiometry, reactions, all that good stuff in the next unit. All right, so first, again, we talk about light. So here in this figure from your book, we have a light source. So this could be a light bulb or the sunlight. And then we focus it through a slit, right? Diffract it through a prism, and we get this continuous spectrum, right? Which your book talks about. And it's continuous in that we see every single wavelength, right? It is continuous in that we see every single wavelength, right? There's not like red and then space orange and then space yellow, right? It's red blends into orange, blends into yellow, right? And so it's a continuous spectrum. We see every single color and every shade of every color, okay? And it's the same principles like a rainbow. Rainbows work the exact same way as we see this, except instead of a prism, right? It's raindrops, okay? Now, if we take a look at this figure from your textbook, right, this just sort of gives us a big picture view of the electromagnetic spectrum, also known as light, right, or radiation, right? All those words go together, okay? So if we take a look at this and let's try to tease out some of the pieces. So first of all, here we have representations about the respective energies, right? High energy, low energy, and respective wavelengths, okay? Now, I don't expect you to have memorized that gamma rays run from 10 to the negative 11th to 10 to the negative 15th, right? I don't expect you to memorize that. But I do expect you to know that gamma rays are highest in energy, followed by X-rays, followed by UV, followed by visible light, followed by infrared, microwaves, and then radio waves, right? And I do expect you to know some basic use or application of each of those types of radiation, okay? In terms of trying to remember how the spectrum is organized, right, so you get your gamma, X-ray, ultraviolet, right, ultra as a prefix meaning, right, beyond, right, so ultraviolet means beyond violet. Oh, look, here's violet, that's the first part of that visible spectrum, right, and then we've got infrared, infra meaning below, right, and that's right next to the color red, and this, right, goes in that pattern that you guys learn when you guys are kids, right, across the street somewhere, right, that Roy G. Biv, right, which helps us to just keep our colors organized, right. So anyway, like I said, no expectation that you've memorized the exact wavelengths of each area, but that you can talk about which ones are higher, which ones are lower in energy, and some applications or uses of each, okay. Now, let's talk about some light from a quantitative perspective, right? So your book doesn't go into these, so make sure you take good notes here, right? These are the video notes that you're supposed to have in your outline, right? So here, this you learned back in middle school. So this is the speed of light, and you should remember from middle school that that is 3.0 times 10 to the 8th meters per second, or we could rewrite that the way we've talked about all year, right? Meters equals 1 second, right? Either way is fine, but that's the speed of light. That is the speed at which all light moves, right? So every single type of radiation on this page moves at that exact same speed, okay? Now we go into the variables that can define it, right? Here we have lambda, right? Which looks like this, right? It's like that, and this is our wavelength, right? And if we think about the units of speed of light, what is wavelength probably measured in? Right, it's probably measured in meters, and that's our wavelength. That is the distance, if we think about some waves, that is the distance from crest to crest, or trough to trough, however you'd like to look at it, but that is the wavelength, right? Here we have frequency. And that is how many waves are in a 1 second window, okay? Frequency, kind of like how frequent is it, right? How many waves show up in a 1 second window, right? This is called hertz, right? As in 50 megahertz or 10 hertz, right? But when we see hertz, we should say, that means 1 over seconds, okay? Hertz means 1 over seconds, just like capital M molarity means number of moles equals to 1 liter, right? This means when we see hertz, we should be like, that means 1 over seconds, okay? And so what this means, right, thinking back to things you guys have been learning for ages in math class, right? If the product of wavelength and frequency must equal a constant, because again, it is a constant, right? This is the speed at which all light travels, right? Constant. If the product of those two values must be a constant, what type of relationship do they have? Right, they are inversely or indirectly proportional, right? In that as one of those pieces of information goes up, the other one must go down if their product must equal a constant, right? If we look over here to this other equation, right, we've got E, which is our energy, same thing we've been talking about all year, measured in joules, okay? And note this is joules per photon. So if we were being really specific, right, we could say joules equal to 1 photon, right? And that would be more accurate, right, than just joules. But that's our energy of any particular light. H is Planck's constant. And again, it says constant, which means it's constant, means it doesn't change. It's always the same value for all types of light. 6.626 times 10 to the negative 34th joules times seconds, okay? And then we have this, which, oh my gosh, this is the same thing we talked about over here. Same exact thing, right? So if we look at this and we wanted to talk about the relationship between energy and frequency, right? What's an easy way to do that? Thinking about math things you guys know. Right, we can isolate the constant, yes? Isolate the constant. If we were to isolate the constant, we would have E over nu equals H, right? This is a constant. So what that means is that E is divided by frequency, which means that if the division of those two things must always equal a constant, if one of those terms gets bigger, the other term must, right, also get bigger, right? So if we're ever trying to analyze the relationship between some variables, it's sometimes helpful to isolate the constant because then that allows us to easily tease out relationships that we are able to figure out, that it just makes it easier, okay? Now, looking at these equations, right, we can tease out one more equation between energy and wavelength, right? We can write a relationship for energy and wavelength using your math skills. Think about it, see what you can come up with, and bring that to class next time. All right, thank you for listening. Be good, and we'll do lots of practice. All right, be good. See you soon. Bye.